Okay, in this video, I'm going to go through the AQA A-level chemistry paper. This is paper 3, and it's the synoptic paper and it is the 2019 one. Okay, I'll do the first half of the paper in this video and the second half in a later one. Okay, so sodium thiosulfate reacts with dilute hydrochloric acid as shown in the equation. Give the simplest ionic equation for this reaction. Okay, so we know that sodium always exists as an Na+, always ionic compounds. So we're going to have, it's going to be 2 Na plus for that. And that means that the charge on the thiosulfate ion, if you don't know, you can work it out that it must be 2 minus, S2O3 2 minus. HCl is a strong acid, so completely dissociates into H2H plus ions and 2 chloride ions. Sodium chloride is an ionic compound, so that's going to be 2 Na plus and 2 Cl minus. SO2 is covalent, so that's just SO2. Sulfur, obviously, is just S, and water is covalent, so that's H2O. Now, for the simplest ionic equation, we need to get rid of any spectator ion, so that anything that doesn't appear, that appears on both sides of the equation without changing. So that's the sodium ions and the chloride ions. So there is the simplest equation there when you cross those out. Okay, SO2 is a pollutant. State the property of SO2 that can cause pollution when it enters rivers. Okay, it is an acidic gas, actually a Lewis acid. Obviously, it can't be a Bronsted-Lowry acid because it hasn't got any hydrogen in it. It's an acidic gas. An equation to show how it reacts with water. Well, SO2 reacts with water to form the weak acid H2SO3. So that's your period 3 oxides part of the syllabus. That's where that comes from. H2SO3. That is a weak acid. We'll just aqueous liquid and gas. Right, so here we've got a shapes of molecules. So from the stuff that you probably did in year 12, draw a diagram to show the shape of the molecule of H2O, include any lone pairs of electrons. Well, we obviously wouldn't draw the dot cross diagram, but just in case you wanted to draw it and cross it out, you can see oxygen is in group 6. Then he's drawn 2 dots for the oxygen, so I need to draw 4 more, 2 lone pairs. So you can see water has got 2 bonding pairs and 2 lone pairs. So that is 4 altogether, 4 pairs of electrons. So the shape of that is going to be tetrahedral with respect to the electron pairs. And of course, we should have a bond angle of 109.5 degrees, but the lone pairs cause mere repulsion. So that goes down to usually quoted as about 104.5. Okay. So draw the shape of the molecule of H2O. So I think if you just drew that is planar. They're all in the same plane though, so you can draw them flat. But you do have 2 lone pairs, so we're going to draw 2 lone pairs there. And the bond angle here is 104.5. Show the shape. We don't actually explain the shape. I think what we need to say whenever in these sort of questions, you always need to say that pairs of electrons repel each other, which is kind of, you may feel like it's stating the obvious, but it's usually in a mark scheme. Pairs of electrons repel each other. You get more repulsion, greater repulsion, sorry. From between lone pair. Then you get between lone pair, bond pair. And that is in turn greater than the repulsion between 2 bond pairs. And so that is why the bond angle is not 109.5, as you would expect for tetrahedral. It's reduced to 104.5. 4 marks there, probably 2 for the diagram, 2 for the explanation, I probably would have thought. Okay, here's about a rate of reaction. Now, the initial rate of reaction between sodium thiosulfate and hydrochloric acid can be monitored by measuring the time taken for a fixed amount of sulfur to be produced. Now, this is the disappearing cross experiment, and it is one of the required practicals. I think it's required practical 3, and that's why they're asking you about it in paper 3, because of course there's quite a bit of practical content in the paper 3. Right, so what we're going to do is describe an experiment to investigate the effect of temperature on the initial rate of reaction. Okay, outline a brief outline of the method, how you measure the time for a fixed amount of sulfur to be formed, how you will present your results in graphical form, and a sketch of the graph that you would expect. Okay. Right. Right, 6 marks. You don't want to go into the details of the practical too much. Basically, what you're going to do is you are going to, each time you're going to get, so to keep it a fair test, you're going to use the same volume and the same concentration of sodium thiosulfate solution and also of hydrochloric acid. Okay, so you're going to get 2 beakers of, you're going to get your thiosulfate in one. You're going to get your hydrochloric acid in the other one. And you're going to place those 2 in a water bath to reach the required temperature. Let them get up to whatever temperature you want. And then you're going to start the reaction by you're going to mix them. And you're going to start the clock. You're going to put the beaker that you do it in over a cross. And you're going to look above the cross, like so. That's supposed to be an eye. And you're going to time how long. So that's the brief outline of the method. Now we're going to, how do you measure the time taken? So we're going to time how long for the cross to disappear. So you can't see it anymore because due to the cloudiness of the sulfur being produced in there. It's a solid. Okay. Now you're going to repeat that probably for 5 different temperatures. I'll probably do one at, say, ranging from about 5 degrees C, which you can do with ice, put them in an ice bath, up to probably about 60 degrees C. So 5 temperatures in the range there. Now, how will you present your results in graphical form? Okay. Now I would probably, right, it says here we need to work out the initial rate. Okay, so we need to work out the rate from the time taken. Okay, so it's important to do that. And so we know that the initial rate of reaction is going to be inversely proportional to 1 over the time taken to go cloudy. So how are you going to process those results? So you're going to say that rate is equal to 1 divided by the time taken in seconds. If you want to, quite often people do, instead of doing 1, it can be any number at all. If you do 1,000, then you get nicer, sort of bigger numbers rather than decimals to work with, so that's fine. We're going to rate is equal to 1,000 over the time taken in seconds, and that's going to be in arbitrary units. And then you're going to plot that against, you ask for a graph, so you're going to plot that against the temperature. Okay, so if you did that, here's your axis, you're probably going to put the temperature on the x-axis. That's the independent variable. And you're going to have your rate here, the y-axis, which is equal to 1,000 over the time. Now the graph you get would be it wouldn't be a straight line. You're going to get it will actually be an exponential. You'll get something like that. Okay, so as temperature increases, you proportionally get a much, you get, for a small increase in temperature, you get proportionally a much bigger increase in rate of reaction. Okay, for 6 marks, that's all you need to say there. Obviously, you don't need to go into the Arrhenius equation for this, for that. It doesn't ask you to work out activation energy, so you're not going to get any extra marks for going into that. That's all you need to say for that, I think. As I say, that is required practical 3. That's what that question is all about. Okay, now sulfuric acid and its salts. Okay, draw the displayed formula of a molecule of H2SO4. So this comes up in organic chemistry and it comes up in inorganic chemistry. So you should know the bonding in sulfuric acid. We use sulfuric acid a lot in, for example, electrophilic addition of alkenes, and you need to know the displayed formula of sulfuric acid to be able to draw the mechanism for that. Okay, right, there we go. 1 mark for that. Sulfur forming 6 bonds there. Right. In aqueous solutions, sulfuric acid acts as a strong acid. Okay, the H2SO4 dissociates to form hydrogen sulfate ions, so it gives away 1 proton. Okay, and the HSO4 ions act as a weak acid. Now, normally, when we presume that the HSO4 actually acts as a strong acid, don't we? We presume that completely dissociates usually, but in this question, they're saying, no, let's treat it more correctly as a weak acid. Okay, so let's do this then. Right. Okay. Given equations to show each stage in dissociation of sulfuric acid in aqueous solution, include appropriate arrows. So this, are we putting in reversible or irreversible? So the first one is H2SO4. It's a strong acid, so we're going to just put a one-way arrow, assuming complete dissociation to form hydrogen sulfate ion and H+. Okay. Equation 2. HSO4 minus, right, that's reversible because it's only a weak acid, they're saying. It gives the sulfate ion and another proton. Okay. Okay, a student is required to make 250 centimeters cubed of an aqueous solution that contains an accurately measured amount of sodium hydrogen sulfate. Describe the method the student should use to make this solution. So this is, again, another practical question. This is required practical 1, the first one, making up a standard solution. 1A, make up the standard solution, and 1B, you do the titration with that standard solution. Right, so what should you do? Right, so you get a sample bottle. With the approximate amount, the approximate mass that you need for your solution, whether you need 1 gram or 1.5 grams, so you put about the right amount in there. Okay, then you weigh the sample bottle with the chemical in it. Then you tip the sodium hydrogen sulfate into a clean beaker. And then you reweigh the sample bottle to find the mass of the stuff you've added by difference. Okay, so you've done that. And now the next thing to do is we've got our beaker, probably a 250 beaker with a little bit of the sodium hydrogen sulfate in there, approximately the right amount. So you've got your solid in there. Then you want to add to there about 100 centimeters cubed of distilled water. Not 250 because you've got to add rinsings afterwards, remember. Add 100 centimeters cubed of distilled water, dissolve, stir. That's a stirring rod. Then importantly, then they really do want you to use this word. You transfer that to a volumetric flask. There's my picture of a volumetric flask. You've usually got to use that word to get the full marks. Volumetric flask, 250 volumetric flask. So you add your solution. Then you're going to add rinsings. Okay, so you rinse the empty beaker, which will have little bits of liquid tiny. You add rinsings to this flask. And then you're going to make up to 250, make up to the mark with distilled water, little markers there. And finally, when you've done that, I think it's pretty important to say that you should put a stopper in it there, and you should mix it by inverting several times. If you don't invert it, it won't mix up properly. You won't have a uniform concentration there. Mix by inverting several times. That is the method. Sometimes that's a 6-mark question. It's only 4 marks there. That's all the things you need to say. Okay, right. A solution that contains 605 milligrams of sodium hydrogen sulfate has a pH of 1.72. Right, now we've got to calculate the Ka of the hydrogen sulfate ions behaving as a weak acid. Okay, right, and state the units of Ka. So what I will do first of all is I'll write down the expression for Ka here. Well, let's write the equation down first of all. So we're going to have the HSO4 minus ion, the sulfate, the sodium is obviously a spectator, I would ignore that. And that's going to give us SO4 2 minus, that's the conjugate base, and H plus. If you like, that's HA, and then this is kind of A minus. So Ka is going to be equal to, I'll do it over here actually. Ka is equal to the concentration of the sulfate ions, H plus ions, divided by the concentration of the weak acid, HSO4 minus. Now, what are the units of Ka going to be? Well, you have got mole per decimeter cubed. The sulfate ion concentration is measured in mole per decimeter cubed. The hydrogen ion is measured in the same thing. And the hydrogen sulfate ion is measured in the same thing. So we cross those out. So the units of Ka are mole per decimeter cubed, and that's, of course, units of Ka are always that. I'll just write that down. So that's the units mole per decimeter cubed. Now, how are we going to do that? Right, first of all, let's work out the moles of hydrogen sulfate we are going to have here. Okay, so we've got the mass, and so we can work out the moles. Well, the MR of that, if you work it out, is 120.1. Okay, so let's do our moles of sodium hydrogen sulfate, which is of course the moles of the hydrogen sulfate ion. We'll do that. That's going to be mass. Let's do it. NaHSO4. Mass over MR. The mass is 0.605 grams. So convert milligrams to grams by dividing by 1,000. Divide by the MR, which is 120.1. That gives us 5.037 times 10 to the minus 3. Right, now we need to work out the concentration, or concentration of the hydrogen sulfate ion. Do that here. We need to work out that H, the initial concentration of it. It's going to be moles over volume. So that's going to be 5.037 times 10 to the minus 3. The volume is 100 centimeters cubed. That's 0.1 dm cubed over 0.1. So the concentration is going to be 0.05037 mole per decimeter cubed. Okay, now, right, we've got to work out Ka here. All right, so let's see what's happening. So what we're going to write down, we're going to write down the initial concentration of these things, initial concentration. Now we've just worked out the initial concentration of the hydrogen sulfate ion is 0.05037. And we're going to say the concentration of SO4 is 0. The concentration of H plus we're going to say is 0. It's not quite 0, of course, because distilled water does contain some, but we can ignore that because it's going to be much lower than the amount we're going to get released from the weak acid. So we'll do that. Right, let's do like at equilibrium then. Equilibrium concentration. Well, we're going to say that the concentration of this has decreased by an amount X. Okay, so that means the concentration of SO4 must be X, and the concentration of H plus must also be X. Right, what we're going to do now is put those numbers into into the equation. Now we can work out what X is, H plus here, because they give us the pH. Look, they tell us it's 1.72. Okay, so we know there that H plus is equal to 10 to the power of minus pH, which is 10 to the power of minus 1.72. And that is, doing the calculator, that gives us a value of 0.01905. Mole per decimeter cubed. And that's, of course, that's X. Okay, so now we can work out these real values here. So we're going to do that. Okay, so 0.053, this is going to be 0.05037 minus 0.01905. And that gives us 0.0313. Okay. We know that X there, we just worked that out. That's 0.01905, and that's that one there as well. Okay, now we've got to put those numbers into this equation up here, okay, to work out Ka. So let's do that. So Ka, I'll do it in a different color. Just put those numbers in. This is the concentration of the sulfate ion. That's 0.01905 multiplied by the concentration of the H plus ion, which is the same. So that's going to be squared, divided by the concentration of the hydrogen sulfate ion, which is that, okay, 0.0313. And that, putting numbers in the calculator, we get a value of 0.0116, the three significant figures, that is, mole per decimeter cubed. Okay, now that's the Ka. Now, if you just, it doesn't actually, that's the answer to the question, but just incidentally, if you think of the Ka of ethanoic acid, well, the Ka of ethanoic acid is like, it's about 1.7 times 10 to the minus 5 mole per decimeter cubed. So you can see this is a weak acid, but it's a pretty strong weak acid by our normal standards. Also, another thing I want to say here is, usually when you do these sort of calculations, see this X term here, right? You normally just, you don't usually do what I've done there. You normally just say that 0.05037 minus X is approximately equal to 0.05037, because X is usually much smaller than that for most weak acids, because this is a borderline weak strong acid. That X is actually quite big there, and they expect you to actually take that. And if you look at the mark scheme, if you don't subtract this here, and you'll get an answer which is not the one they get, and you'll lose some marks. So a bit mean there, because normally we do just ignore that term. We normally do, that's exactly what we do. We say that is approximately equal to, just, you know, X is so much smaller than the other thing. Anyway, there we go. Right. 2.5. Some sodium sulfate is dissolved in a sample of the solution from 2.4. Explain why this increases the pH of the solution. Right, now we have got this weak acid equation. Okay, we've got that weak acid. Now we are going to add some that reaction can go backwards and forwards. So that means this species is a weak acid, but it also means that sulfate is actually a weak base, a very weak base. So if you add a bit of SO4 minus, you're increasing the concentration of the weak base. Le Chatelier tells us if you add some extra SO4, it's going to try and reduce it. How can it reduce it? By combining with that H plus, going backwards. So the H plus concentration will decrease, and so the pH is going to increase. So let's just, what would I write down for 2 marks? I write down that SO4 minus is a weak base. It reacts with H plus to form HSO4 minus, and that is going to lower the H plus concentration and make the pH rise. Okay. Right, now we're on to electropotentials. Okay. So figure 1 is the cell used to measure the standard electropotential for the Fe3 plus Fe2 plus. Okay, so obviously to measure the standard electropotential, you need the standard hydrogen electrode, and that's what we've got on the left here, the standard hydrogen electrode. Okay, what do we have? What is the, so before we answer these questions, what is A? Well, they ask us that. It's the salt bridge. So you're going to have some kind of like cotton wool soaked in, perhaps cotton wool. This is in a glass tube there, cotton wool soaked in potassium nitrate or something. Again, this is another required practical. This is to set up, well, you don't use a standard hydrogen electrode, but you do set up a cell. The purpose of well, let's do it. Purpose of A, what's it for? It's to it's a 1 mark question. It's to allow ions to move to complete the circuit, I would probably say. They don't want for 1 mark, a great big long explanation there. Okay. Right, and then I think it's going to ask us what B is, probably. The substance used in electrode B, right, this is going to be platinum. We always use an inert platinum, isn't it? If you think about, in this, we've got Fe3 plus. That's not a metal that can conduct electricity, the metal ion. We're going to have Fe2 plus in aqueous solution, so we are going to need platinum to conduct electricity. Okay. Complete table 1 to identify C, D, and E, and include the essential conditions for us. Okay, for each. Okay, C, D, and E. So let's go back to the diagram and do it that way. Right, C is going to be hydrochloric acid, not sulfuric acid, and the concentration for the standard conditions, it's got to be 1 mole per decimeter cubed and 298 Kelvin. This is the standard hydrogen electrode. D, well, that's going to be hydrogen gas going in there. And that's got to be at 1 atmosphere pressure for standard conditions. E, well, E, I'll do that in a different color. We're going to have Fe2 plus ions in solution and also Fe3 plus ions in solution, a mixture of those 2 ions. And the standard conditions are both 1 mole per decimeter cubed. And why not put 298 Kelvin in there as well? Okay. So that's what we need for standard conditions. Okay. Well, I've drawn it again down here. I've forgotten I've done that. Okay. So that's right. Right. The standard electropotential for the Fe3 plus Fe2 system is plus 0.77 volts. Okay. Give the ionic equation for the overall reaction in the cell in figure 1. Okay, so what we're going to need to do is write down the 2 equations. So the equation for the ion one, you always put the oxidized on the left, remember, is Fe3 plus plus an electron, reversible if you like, Fe2 plus. And for the hydrogen electrode, well, the oxidized form is H plus ions. 2 minus, and we're going to have the reduced form is H2. Now the electrode potential for that is plus 0.77 volts, and this one is 0 volts. Okay. Right, give the ionic equation for the overall reaction. Right, so we need to see which way it's going to go. Right, which is the most positive one is obviously the iron one. Now this is the most positive, that's the best at taking in electrons. So that is going to go forwards. That's going to be the direction of that reaction. This is the most negative one, the hydrogen one. So that's best at giving away electrons. So that's going to go that way. And then we have to be careful there because we need to multiply this one by 2 before we write the equation, because there's 2 electrons involved in the hydrogen, only 1 in that one. So let's write the equation there. So it's going to be 2 Fe2 plus H2, and that's going to form 2 Fe3 plus and 2H, sorry, around, that's going to be Fe3 plus there. So the Fe3 plus is going to be reduced to Fe2 plus by the hydrogen, and it's going to be 2H plus. Okay, that's the overall, that's the ionic equation there. And state the change that needs to be made to the apparatus to allow the cell reaction to go to completion, right? You need to allow electrons to flow, and so you need to get rid of that voltmeter because that's very high resistance, and it won't let electrons flow. And so you need to replace the voltmeter with just a wire. Okay, you need to have some kind of electrical connection there, obviously. So replace the voltmeter, or short circuit out the voltmeter. Okay. Otherwise, no electrons will flow. Right. A student set up a cell as shown in the representation there. So we've got zinc and zinc 2 plus on the left-hand side and copper 2 plus on the right-hand side. The student measured the EMF E cell with different concentrations of copper 2 plus ions and Zn2 plus ions. Okay, now this is like actually involves something called the Nernst equation, which is not on the specification, but it's how E cell changes as concentration of ions changes. But you don't need to know any of that. You just need to put the numbers in. Okay, complete the table 2 to show the missing value from experiment 4. Right, so we need to do, I've done it, the answer is 2.31. So what did we do there? We did the concentration of zinc, which is 1. So we do 1 divided by the concentration of copper, which is 0.1. And that's equal to 10. And then we have to do ln of 10, natural log of 10, which is 2.31. Okay, that's that there. And they've done it for all the other 4 experiments. They've done it for us. Okay, now we need to plot a graph of how E cell changes as the ratio of these 2 ions changes. So we learn Zn2 plus, copper 2 plus on the grid. Okay, so what we're plotting then, we have got to plot this on the y-axis, and we've got to plot this on the x-axis. Now they've given you this grid here, and I've drawn the graph and I've plotted all the points. Okay, now the piece of graph paper that they give you in the answer booklet is exactly if you don't use that scale that I have used there, they will say that you haven't used up all the graph paper, and they'll knock a mark off for that. Okay, so if you end up in these sort of questions, if you only end up using like half of the graph paper, if your graph is, you've got big graph paper there and your points are all down here, be careful of doing that. You'll definitely lose a mark. Okay, you look in the mark scheme. Right, so I have plotted the graph there. What does it ask us to do? So we've done that. I plotted my points. Now it asks us to work out the gradient. Okay, I think in the next question. Okay, so this equation, the equation shows how E cell varies with the concentration of the reaction. Okay, the equation is in the form, the equation in the form of a straight line, y is equal to mx plus c. Calculate the gradient of your plotted line. Okay, so let's do that. Right, let's just see how we're going to fit this into y is equal to mx plus c. So if I put okay, so we're going to plot E cell is going to be y on the y-axis. X is going to be this value here of ln the ratio of the ion concentrations. Yeah. M is going to be simply this number here. And C is going to be the standard value of the electrode potential. Okay, up there. Right, now, so we are going to, it says calculate the gradient of the plotted line and use the gradient to calculate T. Well, how are we going to do that? We'll look here, this yellow box here. Yeah. We said that M is equal to minus 4.35 times 10 to the constant multiplied by T, the absolute temperature. We're going to calculate M from our graph and look, just rearrange that equation. We should be able to calculate the absolute temperature T. So let's now work out M, the gradient. I'll do that side here. Now, I've done here the change in the y-axis, delta y. Well, we have got right up there, we've got 1.16, and down there we've got 1.04. So I'm going to do 1.04 minus 1.16, which gives us minus 0.12 volts. Now let's work out delta y, changing the y, sorry, changing the x, beg your pardon. Right, so I'm going from there, which is 4.8, to there, which is 4 minus 4.4, so that's plus 4.8. So 4.8 minus 4.4 is equal to 9.2. Right, M is equal to the change in y over the change in x. Change in y is 0.12 volts minus 0.12 over the change in x, which is 9.2. That gives us minus 0.013. That's our gradient, okay? Now we're going to have to put that gradient into this equation here. So M there, yeah, that's the value of that is 0.013. So let's do that and we can work out T. So just rearrange this equation so we get T is going to be equal to M over, sorry, minus M over 4.353 times 10 to the minus 5. Let's do that. M is minus 0.013 over that. That gives us 302 Kelvin. The temperature is the absolute temperature, it's in Kelvin. 302 Kelvin is our answer there. Okay, so that may be a slightly off-putting question because that all that stuff is not on the specification, but it's just a matter of using your mathematical skills. You know, you use this linearization of lines before with the Arrhenius equation, various other places, and it's just a matter of putting the numbers in. Okay, I think the next thing is going to do is ask us to work out what E, or what E, the standard value is. Okay, now the standard value is the intercept on the y-axis. Okay, and you can see there, yeah. C is E cell. So what is the value at here? The intercept is here at 0. The E cell value is, well, that's at 1. That's going to be at 1.10, isn't it? Yeah. Okay. I don't know whether it does ask us that actually. Okay. Next question, 3.8 then. Make this a bit bigger, sorry. Okay. In experiment 2 in table 2, the electropotential of the copper 2 plus copper 1 plus electrode is plus 0.33 volts. Use the data from table 2 to calculate the electropotential for the zinc electrode in experiment 2. So we're looking at experiment 2. The E cell in experiment 2 is 1.13 volts. Okay, now we're going to use the equation E cell is equal to the E right minus the E left. We want to find out the electropotential for the Zn. Right, Zn is the right hand one, so I'm going to rearrange that. So E right is going to be equal to E cell minus E left. E cell, they tell us, is there in experiment 2 is 1.13 volts. And E left is plus 0.33 volts, so minus 0.33 volts. And that gives us a value of 0.80 volts. So that's the electropotential of the zinc thing. Why is the value different from the standard electropotential for the zinc one there? Right, it's because if you look at the concentration of zinc ions in experiment 2, it's not 1 mole per decimeter cubed, it's 0.1 mole per decimeter cubed, so it's not the standard value at all. Okay, that's why you don't get, it's not the same as the E cell. It's not in the standard conditions. Okay, so leave the end of the electropotential question now and straight on to organic. Ethanol reacts with potassium cyanide followed by dilute acid to form 2-hydroxypropane nitrile. Right, name the mechanism for the reaction between potassium cyanide and ethanol. So if I just write down here, so we've got ethanol is going to look like this. And the potassium cyanide, well, the species which reacts is the cyanide ion, which is a nucleophile, and it's going to be attracted towards that. That's the first step in the mechanism. It doesn't ask you this, but that's going to go, that pair of electrons is going to go there, and this pi bond is going to break. So that pi bond is, we're breaking a double bond, it's addition, and it is nucleophilic addition. Here's the answer for 1 mark. Okay. The 2-hydroxypropane nitrile formed by the reaction in 4.1 is a mixture of 2 isomers. Okay, and these are going to be stereoisomers. Okay, and so you're going to get 2 stereoisomers. Explain how the structure of ethanol leads to the formation of 2 isomers, and draw 3D representations to show the relationship between them. Right, now it doesn't ask us to show to do this, but I am just going to just draw the product. What is the product going to look like? Well, what happens there? If that reacts, that reaction mechanism continues, you're going to get CH3, CO minus, the cyanide there, a hydrogen there, and the O minus is going to pick up a proton that will eventually become OH. So what we've got there is we've got a carbon atom here with 4 different groups attached to it, and so it can show optical isomerism. Okay, and when we're going to get a 50-50 mixture, what's that called? This 50-50 mixture of the 2 optical isomers is called a racemic mixture. Right. Explain how the structure of ethanol leads to the formation of the 2 isomers. So I'm going to annotate here. I'm going to say, right, ethanol around this carbon atom here is the carbon is planar. Bond angle is 120 degrees, so it is flat. Okay, and the the cyanide can attack from above or below. If it attacks from above, you get one isomer. If it attacks from below, you get the other isomer. So the structure of ethanol is essential there to say that the carbon-alcarbon is planar, is flat, and then leads to the formation of two isomers. The ligand, the cyanide nucleophile attacks from above or below, both are equally likely. Attacks from above, you get one isomer, attacks from below, you get the other. Draw 3D representations of the two isomers. Now they are optical isomers. They're non-superimposable mirror images of each other. So I'm going to draw one of them here. So here's I'm going to draw. So we've basically got to show that that's tetrahedral, this carbon here. So circle it. So 4 different groups. I've got an OH there. Let's say we've got a CH3. That's in the plane of the paper. We've got the cyanide group coming towards us, and we've got the hydrogen going back into the plane of the paper. Okay, so that's one isomer. I'm going to draw my imaginary mirror line there, and the other one is a non-superimposable mirror image. So this time we want the hydrogen going in there, we want the cyanide coming out, we want the methyl there, and the OH there. Okay, that's our 3D representations of the two isomers. Okay, and it might be worthwhile stating there that they are non-superimposable mirror images, because it says the relationship between them, non-superimposable mirror images. Okay, 2-hydroxypropionitrile can be used in the synthesis of the monomer acrylonitrile. Suggest a suitable reagent to convert it. Okay, so let's draw what have we got as the product here. We have got double bond there. Okay, what do we start off with? So that the starting product, we had CH3. Cyanide group and an OH. Okay, so you can probably see what we've done there is we have dehydrated an alcohol essentially. So we've taken removed the OH group and the hydrogen from the carbon next door to create a double bond. Right, reagent and conditions. And what are the reagents? Is you need concentrated phosphoric acid or concentrated sulfuric acid. Phosphoric acid down, and you need to heat with reflux. Basically, you need heat, and if you don't reflux, you lose the products because they're volatile. Okay, so that's 2 marks there, one for the phosphoric acid, one for the heat with reflux, I think. Okay, draw a section of the polymer polyacrylonitrile showing 3 repeat units. Okay, so I'm going to draw that above here. So what happens is we are going to get, here is our monomer. And this is an addition polymer, isn't it? Okay, so what's going to happen here is, right, we're going to break the double bond and we're going to form a new bond there. Okay, so I need to rub out those. I've only drawn 2 repeat units there, so I need to draw another one. We'll do the same thing again here. Like that. Okay, that is 3 repeating units. Addition polymer. Right, now that is as far as I'm going to go with that paper. I'm going to do the next half in the next video.